All right, hello there. We're going to do section 14.4. We're only going to do part of the notes here, and we'll finish the rest in class. So you know from single variable calculus that a tangent line is a good approximation of a curve in a small interval, all right, or at a certain point usually, or around that point. If you zoom in toward a point on a surface, because it's 3D now, that is the graph of a differentiable function of two variables. The surface looks more and more like a plane. Like if you put your face up against even like a basketball, it kind of looks like flat to you because your eyeball is so close to it. So it's called its tangent plane. Okay, so, and we can approximate the function by a linear function of two variables. So we're going to do that. We're going to, instead of having an equation of a tangent line, we'll have the equation of a tangent plane. So you can see that in the picture over here, kind of based off of the picture from last time. Okay. All right, so equation of a tangent plane. First of all, remember that equation of a plane looked like this. It was always, a x minus x0 plus b, y minus y0 plus c, and then z minus z0 equals 0. Remember that a, b, and c were the direction, and then you had your x0, y0, and z0 were your point. And so you're going to see that also in this format. It's going to be changed around a little bit, but it's pretty you're going to notice similarities. All right, so suppose a function has continuous partial derivatives. An equation of the tangent plane to the surface, z equals f of xy, is at a certain point is going to be this: z minus z0 equals fx, so the derivative with respect to x, and then you'd have x minus x0 plus fy, the derivative with respect to y at that point. So you have to plug in the numbers to the derivative if you are doing it at a certain point, and y minus y0. So that should make a little bit of sense because your directions in the x and the y direction are your derivative directions, and you have no direction in the z direction, so that's why z doesn't have one. All right, so we're going to do this here. Find the equation of the tangent plane to this equation at the point 1, 2. So even though they give you 1 and 2, you always have to find the z value. So 1 and 2, so I would plug in 1 and 2 into here and here. And when you do that, you get 12. So 1, 2, 12. So even if you aren't given that, you have to find it. All right, so I need fx and I need fy. So if I look across there, the derivative of z with respect to x is negative 8x. And with respect to y is negative 9y squared. Okay. So, and if we plug in their numbers 1 and 2, because that's the point we're trying to do this at, so I go ahead and get negative 8 for my fx, and I get negative 9 times 4, so I get negative 36 for that one. So I'm just going to plug it in. I get z minus 12, because that's the z0. Then I have negative 8 times x minus 1. And then minus 36, because it's a negative, my fy up here is negative. Then I have z minus, that would be y. Y minus 2. All right, so you clean that up a little bit, and you could leave z minus 12. Over here I get negative 8x plus 8 minus 36y plus 72. And maybe if you like to get all the x, y, and z on the one side so it looks more like a plane to you, you would have 8x plus 36y plus z equals 92. Or you could leave it z equals or whatever you feel like doing with it. Okay? All right. So this next question comes, it says, where is the tangent plane horizontal? So remember you get that question in calculus last year sometimes, right? Like, where is the equation of the tangent line a horizontal line? Or so when is the slope equal to 0, right? So the tangent plane is going to be horizontal when the slopes of your derivatives are 0. So in this case, we have two of them to deal with. Both fx and fy have to be 0. Okay, so fx, if we figure it out, is going to be 12x squared plus, 6xy. That has to be 0. And fy, which is, 3x squared minus 48, has to be 0. So this is like a system of equations right here. So these both have to be true at the same time. So a system of equations, in a way. Okay, or maybe not in a way, but they are. All right, so I need to solve one, or I could solve one and then plug it into the other. That's one way to do it, by substitution. And I think I will do that here because I clearly see how to solve this. If I move the 48 over, so I get 3x squared equals 48. Then divide by 3, I get x squared equals 16. And then, of course, x equals plus or minus 4. And so then I plug that into the other one, the other equation. So if x equals 4, I get fx would be, let's see, 12 times 4 squared. So 12 times 4 squared plus 6 times 4 times y equals 0. So you work that all out and solve it, you'll get that y has to be negative 8. And then if you do the same thing for x equals negative 4, you'd have 12 times negative 4 squared plus 6 times negative 4y, and you get y equals positive 8. So there you have, let me see if I can make this thing go down. Oh, I can't. Anyway, so I would write my points right here. Sorry about that. Where is the tangent plane horizontal? So the 2 points where the tangent plane is horizontal are 4 and negative 8, and also negative 4 and positive 8. These are the 2 points. That is my answer to the question down there. And if you wanted to find the z value, you would plug it back into the original to get the z value. Okay. All right. So moving right along here, we're going to do the next 3 slides and then stop. All right. So this example here, find an equation of the tangent plane to this graph at the point 1, 3, 12. So I'm going to go ahead and do zx and zy, or fx and fy. All right, so that would be 8x and then y, and this one would be 4x squared if I did my derivatives there. Now I have to go ahead and plug in 1 and 3. So if I do that here, I get 24. And if I do plug in 1, basically, I get 4. Okay, so it's just like we've been doing before. So I have z minus 12. Notice that was given to me here. And then I have 24, x minus 1, plus 4, y minus 3. Okay. So if I work that all out, I get z equals 24x plus 4y minus 24. Okay, so that is the equation of the plane, the tangent plane at the point 1, 3, 12. All right, so the tangent plane, when it comes up, now I'm not going to draw like a plane, but let's say you have this curve there and you have that point where you're doing the tangent plane. So basically you have this plane coming up along that. So any place close to this point, like let's say that you were like right here, well, that's pretty close to the thing we just figured out. So I could use this equation to approximate the value of a point really close on either side of the actual thing that I just did, of this point right here. So that's what's going to end up being called linearization or linear approximation. Okay, so the plane in part A is a good linear approximation or linearization of z, the function, at x0, y0, z0. So use the tangent plane from part A to approximate the function's value at 1.1, 2.9. So notice that's just a little bit different. It's a little bit off. It's a little bit higher here and a little bit lower there, but that's fine. So I'm going to go ahead and use my approximation that I have, my tangent plane. So I have 24, x is 1.1, plus 4, 2.9, minus 24. So when you do that, you get z equals 14. Okay, now remember, it's an approximation. It's about what it is. Because if I actually plugged in these numbers, so do you see that doing all these simple multiplications, like, 24 times 1.1, 4 times 2.9, minus 24, those are very simplistic calculations. Whereas if I had to plug in 1.1 into here and here, that would be a little more complicated, and I would definitely want a calculator nearby. So it's a way to approximate something without doing a lot of big calculations. But if we want to see the true value, we're going to go ahead and find the true answer and show you how it's similar. 1.1 squared and then 2.9. So you plug that into your calculator, you get 14.036. Okay, so you see that it's very close to our fake answer, our approximation, but it's just a thing to do. Okay, all right. So you just learned from the last example is a linear function whose graph of it is this tangent plane. So a linear function who has this tangent plane. Okay, and so basically we're going to call this L of xy, called the linearization of the function at AB is going to be this. So basically what's going to happen over here is this is going to be solved for z. This is going to pop over to the other side. So I'm going to abbreviate this a little bit right here. I'm going to put the function's value at AB, because that's literally what z0 is. So that's pretty much that, plus the derivative with respect to x. So that's this part right here. And then, of course, x minus a. So really it's just a replacement of all the things that we had before. And then plus fy, so the function's derivative with respect to y, and then y minus b. So either way you want to write it, with an L or an f of xy, you are using this to approximate the curve at that point. All right, so this is called the linear approximation. Or the tangent plane approximation of f at AB, which is what we just did on the last page, which you didn't know we were doing. Okay, so this one right here says find the linearization of this function at the point 3, 0. So it turns out that plugging in 3, 0 is not too hard to do here. So if I plug in 3 and 0 into this function, so my function's value at 3, 0 is the square root of 3 plus e to the 4 times 0 would be 0. So it'd be e to the 0, which is 1. So I get the square root of 4, which is 2. All right. So I have the point 3, 0, 2. So we're going to use that to go ahead and find my linearization at 3, 0. And this is going to give me a good way to approximate anything near the point 3, 0. Okay. All right. So first of all, that would involve finding the derivative with respect to x. So remember, this is like saying to the 1/2 power. Oops, plus e to the 4y. I'll go rewrite that. So we're going to need our chain rule. So I do my derivative 1/2. I put x plus e to the 4y back. And I put a negative 1/2 times the derivative of the inside with respect to x. Well, the derivative with respect to x of the inside would just be 1, because there's just one x in there. All right, if I was doing fy, I do the same thing, 1/2 x plus e to the 4y, negative 1/2 times the derivative of the inside with respect to y. So the x is going to go away, but the e to the 4y, the derivative of that, is going to be 4 e to the 4y. So now with both of these, I have to plug in the points 3, 0. All right, so if I plug in 3 and 0, I'm going to get 1/2, 3 inside for x, and e to the 4 times 0, so that's e to the 0, which is 1. So I basically have 3 plus 1, so I have 4 to the negative 1/2, and then times 1, of course. Well, 4 to the negative 1/2, that's 1 over the square root of 4, so that's going to be 1/2 also. So basically getting a 1/2 times a 1/2, which is 1/4. All right, so when I evaluate the next one at 3, 0, notice that I basically have the same thing right here, the same thing that I just evaluated. So I'm just going to go ahead and steal my last answer and put 1/4, because you don't want to hear me blunder through all that again, times 4 e to the 4y. Well, y is 0, remember, so e to the 0. So basically I'm getting 1/4 times 4, and so I get 1. All right, so these values are going to be used for my fx and fy when I do my linearization up in these problems up here. Basically, they're pretty much the same. All right, so I think I'll write a different color so we can see the difference here, but my linearization at 3, 0 is going to be the function's value at 3, 0. So if I plug 3 and 0 into this function, remember that is 2 right here, so it's going to be 2 plus f sub x, so that would be 1/4 x minus 3, plus then f sub y, which is 1, times y minus 0, because that's the y value. All right, so you clean that up, and your linearization at 3, 0, your linear approximation at 3, 0, if you clean that up, you get 1/4 y, or x, plus y plus 5/4. So if you want to approximate something close to the point 3, 0, you can use that. If you literally plug in the point 3, 0, then you will get the answer, which is 2, right? Okay. All right. So there's that, and this is the last page. Yep, this is the last page we're going to do right there, right here. So recall, sometimes it's difficult to tell whether or not a function is differentiable at a point because we have to first check that it is continuous at the point. All right, and this sometimes involves the handful of limits we had to check and see if they had matching solutions back from earlier in the chapter. All right, so here's a theorem that says, it's proven, if the partial derivatives fx and fy exist near AB and are continuous at AB, then the function is differentiable at AB. Okay, so really you don't have to do all those limits anymore. If everything looks continuous and good and you can actually do the derivative, then you're good to go. So that makes us happier. We don't have to check. All right, last one. Show that this function is differentiable at 1, 0 and find its linearization there and use it to approximate f of 1, 1 and negative 1, 0, 1. All right, so when I go to check, I'm saying to myself, if I plug in 1 and 0, there doesn't seem to be a problem there. There's no kind of like asymptotes or like illegal spots. So this thing is continuous. All right, it seems to be continuous there. And let's do f of x, or fx, and fy. If I can do the derivative, I already kind of figured it was continuous. And so if I can do these derivatives, then I'll just go ahead and accept the fact that it's differentiable. Okay. All right. So my derivative with respect to x, I'm going to have to kind of break that up to do, what's it called? Product rule. So the derivative of x is 1 times leave e to the xy alone, plus the derivative of e to the xy will be e to the xy again, times the derivative of xy with respect to x would be y times that original x in front. So this all cleans up to be, let's see, e to the xy plus xy e to the xy. All right, with respect to y, I'm going to, actually I don't really have to break it up because that x out front can just stay there as a constant. And then derivative of e to the xy is e to the xy again, times the derivative of xy with respect to y, so that would leave me another x. So that leaves me with x squared e to the xy. Okay, all right, so when I go ahead and plug in my values, I have to do this at 1, 0. So let's go ahead and figure out the rest of it, 1, 0. So if I plug in 1 and 0 into this problem, let's see, 1 times e to the 0, that would just be 1. So I get 1. All right, so let's put these in the derivatives. So if I put 1 and 0 in these derivatives, for this guy, I would get e to the 0 plus 0, so that would be 1. For this guy right here, my x is 1, and then I have e to the 0, so that's also 1. All right, so my linearization at the point 1, 0 is the z value, so 1 plus fx, which was 1, x minus 1 because of this right here, and then plus fy, which was also 1, and then y minus 0 because the y value is 0. All right, so you clean that up and you just get x plus y. So my linearization at 1, 0 is just x plus y. So if you would like to estimate something close to the point 1, 0, you could just add your two numbers together. So this is my linearization, my estimate of something real close. So I want to approximate f of 1.1 and negative 0.1. So look at how tedious that would be. We're trying to approximate this. How tedious it would be if you had to plug in 1.1 for your x's right here, and you had to plug in negative 0.1 right there. You would definitely need a calculator. You'd be like, oh, geez, I don't know what that is. You had to do e, choose that power and all that. That'd be horrible. But instead, if you wanted to approximate it, all you would have to do is add the x and the y, 1.1 plus negative 0.1. And so that comes out to 1, our favorite number in this problem. Okay, all right, so that's basically it, and we are going to finish the rest of this in class because this is going to be too long otherwise, and I'll see you later.